In section 13.10, we're going to stick with the idea of optimization problems. And in this section, we're going to use Lagrange multipliers in order to solve these types of problems. Many optimization problems have constraints, which are restrictions on the values that can be used to produce the optimal solution. As an example of this, suppose we want to find the rectangle of maximum area that can be inscribed in the following ellipse. So to work this problem out, what we're going to do, this is going to kind of motivate, we'll look through this particular example, and this will kind of motivate the definitions we're going to see in a moment for the Lagrange multipliers. If we go ahead and kind of draw a sketch of this equation, this equation is going to be an ellipse. Its major axis will be vertical, it'll be along the y-axis of length 4, and its minor axis will be horizontal of length 3. So if we draw a sketch of that ellipse, this is what we would get. And we want to inscribe a rectangle in the interior of that ellipse. The question is, what is the largest possible area for such an inscribed rectangle? To start, let's let x comma y be a point, be the vertex on the rectangle that's in the first quadrant. We're trying to maximize the area here. Notice that if this distance is x, then that would be the same as this length here. So the length of the rectangle would be 2x. This distance from the vertex to the x-axis would be of length y. And then from symmetry, so too would this be y. So the width of this rectangle would be 2y. Therefore, the area function would be given by length times width. That's going to be 2x times x times 2 times y, which would be area as a function of x comma y would be 4xy. And this is the quantity that we're trying to maximize. So what should be the locations of the coordinate x comma y in order to give this function the maximum, subject to the constraints that that point has to lie on the ellipse? One of the things that we can do is, let's think of this area function and let's consider its level curves. So that's thinking of where the outputs would be constants for the various values of k. If we look at some of these graphs of these level curves, these ones would fall outside of the boundary region for k equals like things like 72, 56, 40, etc. And we see that the level curves that would just touch the restricted boundary domain would be when k equals to 24 here. So our goal is we want to find x and y such that f of x comma y is a maximum. Our choice, again, depends upon the constraint equation, which is the ellipse. And so what we see is that these level curves represent a family of hyperbolas. If you were to graph these hyperbolas, most of us would probably solve it for y. If you're graphing it as a planar equation, think of it as k divided by 4x. We can graph a bunch of those. And one of the things that we realize is that in this family, the level curves meet the constraint equation when they intersect. Moreover, to maximize, we want to find the hyperbola that just barely satisfies the constraint equation. Obviously, the further out those hyperbolas move, the larger the overall corresponding area. When this happens, the one thing that we want to observe, I'll go back to the figure in a moment, is that the level curve that does this is the one that's going to be tangent to the ellipse. So these level curves here, these, for example, would correspond to a level curve of 72. That was the a of x value, so that's an area of 72. But that wouldn't work because those ordered pairs xy would lie outside of the ellipse. If we back it down, though, this would be the one that's going to work. And what we notice is that at that point, when the level curve intersects the ellipse, that those two curves are going to be tangent at that point. So what does it mean for that constraint equation to be tangent to the ellipse? Well, what this means is that the gradient of f of x comma y is going to be a scalar multiple of the gradient of g of x comma y at the point of tangency. They're not going to be scalar multiples forever. So remember, the idea of tangent means that one is a constant multiple of another. But it's not at all points. It's going to be just at the point of tangency. Okay. This scalar multiple, we're going to denote this via the Greek letter lambda, which looks like this. And this brings us to Lagrange's theorem. What Lagrange's theorem says is that if we have functions f and g that have continuous first partial derivatives such that f has an extremum at a point x0, y0 on the smooth constraint curve g of x, y equals to c, if the gradient at g at x0, y0 is not equal to the 0 vector, then there is a real number lambda such that the gradient of f at the point is equal to lambda times the gradient of g at that point. And we give a special name for this constant. This constant is referred to as a Lagrange multiplier. And keep in mind, in the theorem of Lagrange, this equational condition here is at the point where f has an extremum, x0, y0. It's not for all x and y. So how does the method of Lagrange multipliers work, and how will that allow us to find these maximums, or extremum, I should say? Well, if f and g satisfy the hypotheses of Lagrange's theorem, then let's suppose we want to let f have a maximum or a minimum value subject to the constraint g of x, y equals to c. To find the maximum or the minimum of f, we're going to perform the following steps. We're going to calculate the gradient of f, and we're going to set it equal to the gradient of g multiplied by the scalar lambda. This will give us a system of equations. And maybe I'll be a little bit more explicit here. If you look at the gradient of f, recall what was the gradient of f? Well, this was fxi plus fyj. The gradient of g, similarly, would be gxi plus gyj. And if we're setting those two things equal to each other, then that's saying that at that particular point, fxi plus fyj is equal to lambda times gxi plus gyj. If you distribute and set component functions equal to each other, that says that fx, the partial of f with respect to x, is going to be equal to lambda times the partial of g with respect to x. And comparing the j components, the j component would be fy for the left-hand side, and the j component for the right-hand side would be lambda times g of y once you distribute the lambda through. So that's where those conditions are coming from. And this last one is just the level curve condition. We're thinking of g of x comma y as a constant. We then evaluate f at each solution point obtained from step 1. The greatest would yield the maximum of f subject to the constraint, and the least value would yield the minimum of f subject to the constraint.